Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Okay, let's unpack this. If you're a student pilot, you know this feeling. Flying isn't just pointing the airplane where you want to go. It's about knowing with absolute certainty which way is up and which way is north. And when you're learning, you're often dealing with instruments that demand just constant vigilance.
Exactly. And our mission today is to, cut through that complexity. We're talking attitude and heading systems. We want to give you that shortcut to really being well-informed about the tech that governs your orientation. We're tracking that huge shift from the old mechanical gyros, the ones that could tumble,
right,
all the way to the sleek, modern solid-state sensors that you see in new aircraft.
Yeah, and we've looked at some really detailed sources explaining the whole spectrum. Everything from the cutting-edge attitude and heading reference system, the AHRS, all the way back to the older systems you are probably using in your training aircraft right now. The real goal here is to highlight that operational difference, knowing the instruments that find north for you versus the ones that you, the pilot, have to constantly correct.
And the big insight here is just recognizing that system reliability is everything. It's the difference between a workload you can manage and, potential disorientation. The entire push of modern avionics was to eliminate that one single biggest flaw in the old system, that free-spinning mechanical part that could just hit its limits and give up on you.
The fundamental problem was just mechanical mass spinning inside a frame that was too small for it. And the solution, just get rid of the spinning mass entirely. So let's start there. Let's look at the solid-state system that did it. The AHRS.
The Attitude and Heading Reference System, or AHRS. It's the absolute bedrock of any modern glass cockpit. It directly replaced those, conventional free-spinning gyros that were always bumping up against their pitch and bank limits. Instead, AHRS uses these really advanced solid-state sensors. Sometimes they're laser ring gyros or accelerometers.
So what's the immediate, operational takeaway for the pilot who's flying with an AHRS?
Total freedom. It's that simple. These systems are capable of operating during flight at any attitude. There's no risk of tumbling. Your aircraft can be completely upside down, and that attitude indicator on your screen, it's still going to show you a stable, accurate horizon. And that reliability, it didn't just make flying easier. It practically eliminated a major cause of instrument-induced spatial disorientation, especially in bad weather.
That is a complete game changer. You mentioned the AHRS sends two streams of information to the primary flight display, the PFD. For a student pilot, that's that big main screen with all your critical info. So what are those two streams?
So first, it generates your attitude information. That's your pitch and bank data. That's what creates that artificial horizon on your PFD. And second, and this is crucial, is the heading information. But this isn't derived from the attitude sensors. It actually comes from a dedicated external magnetometer that senses the subtle lines of the Earth's magnetic flux.
So the AHRS is sort of blending two things. It's making its own reliable attitude data, but then it's being fed super accurate heading data from a totally separate source. Which brings us to the core physics of how we find north in the first place, the flux gate compass system.
And what's so fascinating here is that even the most advanced, multi-million-dollar AHRS systems, they still rely on this very fundamental principle of electromagnetism to keep the heading straight.
The basic physics is surprisingly elegant, really. I mean, a classic magnetic compass, it just uses the Earth's magnetic flux to align a physical magnet, right? The flux gate system uses the other characteristic of magnetism. When lines of flux cross a wire, they induce an electrical current. So by measuring that current, the system can figure out its direction without any moving magnet.
And that measurement is done using something called the flux valve. That's the sensor. The flux valve is designed to be incredibly susceptible to that magnetic field. It's a small segmented core of soft iron, which just readily accepts magnetic flux, and it has 3 little detection coils wound around it.
Okay, but hang on. The cockpit is a terrible place to measure a subtle magnetic field. You've got power lines, radios, all sorts of interference. How does the flux gate make sure it's only reading the Earth and not the plane?
That's where the genius of the design comes in. It uses an artificial field. There's a 4th coil wound around the core, and it has a powerful alternating current, usually 400 hertz AC, flowing through it. And this AC, it acts like an electronic shield. It momentarily saturates that soft iron core.
So if I'm getting this cycle right, when that AC current is at its peak, It creates such a strong magnetic field of its own that the sensor literally can't accept any flux from the outside. It's effectively just blocking out the Earth's field for a split second.
Exactly. It saturates the sensor.
Hmm.
But then, as that AC current reverses and drops between the peaks, the core is momentarily demagnetized. And it's in those tiny fractional moments that the core can accept and measure the pure external magnetic flux from the Earth.
Wow, that's brilliant. So it's constantly just turning itself on and off to isolate the real signal.
And that signal is the current induced in those 3 detection coils. As the aircraft changes its heading, the current flowing in those coils changes relative to the magnetic field. This continuously changing electrical signal is what gives you your precise, non-interfered with heading information.
And that signal then goes to a synchro, a little rotational device inside the instrument case, which physically rotates the dial of your indicator. And that leap in precision is what allows you to display that information remotely accurately and combine it with other navigation data.
Which brings us to remote indicating compasses. And this is where that workload reduction really kicks in. These instruments were specifically designed to overcome all those errors and limitations you get with the old cabin-mounted magnetic compasses and mechanical gyros.
The main one you'll see is the horizontal situation indicator, or HSI. It puts your heading, your course selection, and your navigation all in one place.
Right. But the actual control panel for this system is the sleeving control and compensator unit. And this unit has 2 modes, 2 critical modes that you absolutely have to understand.
The first one, slaved gyro, that's kind of the easy mode, right?
It is. It's the automatic mode.
Yeah.
The gyro is constantly being slaved or automatically oriented to the precise magnetic info coming from the flux valve. The pilot rarely needs to touch it. But if something goes wrong, you need to know what that slaving meter is trying to tell you.
Okay, tell us about that meter.
It just shows the difference between the heading on your compass card and the magnetic heading the flux valve is actually sensing. So if it deflects to the right, it means your compass card is showing a heading that's counterclockwise of reality. It's to the left. You might see it deflect wildly during a fast turn, but that's just the system trying to catch up.
And the second mode is free gyro.
That's your manual override. If there's an electrical fault, or you think the flux valve is giving you bad data, you push a button and enter free gyro mode. Now it stops seeking north. You, the pilot, have to use the manual heading drive buttons to align the compass card yourself.
And we know the magnetic sensor, the flux valve, it's mounted remotely, often in a wingtip. Why is that specific spot so important?
It's all about eliminating magnetic interference, completely. The signal is then amplified and sent forward to the cockpit. It's this clean data combined with navigation data that allows for tools like the RMI, the radiomagnetic indicator. That's just a classic instrument consolidation. You get this super accurate flux valve driven compass card. And on top of that, you have pointers driven by your ADF and VOR signals, all on one dial.
That reduction in scanning is so key, but let's pivot back to reality for a second, because many of you, the PPL students, are going to spend most of your initial training mastering the limitations of the older non-slave systems. And that brings us to, I think, what is operationally the most critical section for initial training, the legacy challenge.
Absolutely. Understanding the free gyro heading indicators, the ones without that slaving mechanism, is just non-negotiable. These indicators use mechanical gyros, and physics dictates they are subject to precession.
Yeah.
They just drift constantly.
So the key limitation is pilot responsibility. Every single time. You have to check and manually reset that heading indicator against the magnetic compass about every 15 minutes. If you fail to do that, your displayed heading could be off by 10, 20 degrees inside of an hour.
And here's a critical operational fact that pilots forget. When you are manually resetting your heading indicator, you must only adjust it when the aircraft is flying absolutely straight and level at a constant speed, because the magnetic compass itself is unreliable during turns or acceleration or deceleration. If you adjust your gyro while you're turning, you're just baking that error into your primary reference.
You're giving yourself false confidence.
Right.
Speaking of failures, what about the famous problem of tumbling or spilling?
This is that mechanical limit we talked about at the beginning. On a lot of older heading indicators, the gimbals, the frames holding the gyro, they have physical limits. Usually it's around 55 degrees of pitch or 55 degrees of bank. If you exceed those limits, the instrument physically tumbles. It spills.
And once it's spilled,
It's useless. It stops giving you any useful information. The pilot has to manually reset it, usually with a caging knob, which can take critical minutes, especially if you're suddenly in the clouds. I once heard a veteran pilot describe the moment a gyro spilled in IMC as the fastest way to lose about 5 years of your life expectancy. Modern AHRS, of course, completely eliminated this risk.
And beyond the mechanical limits, you've also got the power source. Most of these older instruments are vacuum-driven, so what happens if that vacuum system fails?
Well, if the vacuum system gives you inadequate suction, the gyro just slows down. And as the gyro's rotational speed decreases, it becomes way more susceptible to deflection. This dramatically increases that precession error. The rate of drift can just accelerate rapidly. So as the pilot, you have to know where your vacuum gauge is or your suction warning light, and you have to monitor it religiously. A low suction indication means you can't trust your gyro anymore.
Which just highlights that for these legacy systems, knowing your instruments is an active, demanding process. Which brings us perfectly to the essential checks a student pilot has to perform before every single flight.
Yes. These steps are immediately relevant to your workflow, starting right at engine start. First thing, as the engine spools up and the power comes online, listen. Listen for any abnormal sounds from the panel. Gyros that are failing often make these grinding or whining noises.
That's the physical check. And then during the taxi, you have to actually test its function.
Correct. While you're taxiing, you should see the heading indicator respond correctly to turns. You turn right, the numbers should decrease. You turn left, they should increase. But also, you need to observe precession. Does it seem to be wandering more than it should? Does it match the runway heading?
And there's one final very important note about that vacuum system check, specifically when you're taxiing or holding on the ramp.
Yes. If your aircraft has an engine-driven vacuum pump, you have to remember that at idle power settings, the pump's output is often reduced. This means your gyroscopic instruments might not be running at their full operating speed until you apply power for the run-up. So don't be alarmed if you see rapid drift while you're just sitting there idling. Instead, understand the system limitation. Your instruments aren't fully reliable until you confirm you've got adequate vacuum suction during your run-up.
So what does this all mean? It means the indication of direction and attitude in an aircraft is this sophisticated dance. It's between physics, magnetics, and electronics. The most advanced systems are using alternating current to isolate the Earth's magnetic field, and the most common trainers are using a tiny spinning wheel that needs you to intervene every 15 minutes.
The key takeaway for you as a pilot is understanding that massive leap in reliability that AHRS provides. It eliminates tumbling, it constantly maintains the correct heading. But even with all the advanced electronics, the systems still rely, fundamentally, on sensing the Earth's subtle magnetic field. And this raises an important question for you to think about as you master the cockpit. How much does that constant need to monitor vacuum levels, listen for weird sounds, and manually adjust a free heading indicator every 15 minutes? How much does that truly influence a pilot's workload and situational awareness, especially in bad weather, compared to a fully automated system? Because at the end of the day, the reliance on basic magnetic principles remains the core of flight navigation, and mastering your system's limitations, whether they're old or new, is paramount.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.